So just look real quick here. Copper lives right here, correct? All right. What copper will do is copper will promote one of these S electrons to completely fill the D shell. It's more comfortable if all 5 of the D clouds are full, but only one. I have 1 more minute because that distraction didn't count, right? All right. What's that? Well, all 5 of the boxes or all 10 electrons are in them. It would be more comfortable that way. So look right now. The only exceptions are here. So they will promote one so that they can have a full complement of D electrons. Okay with that? Do you remember how close the D's and S's were and that there's some confusion with them? They're so close in energy that it's really not that big a deal. It just needs to absorb even the light by being in the planet or a little bit of heat or whatever, and it can promote that electron just a little bit and have a more stable D shell. All right? Now, the super as to why, no one really knows why some of these tiny little minute things happen, but they do. Okay? So, there might, I don't even know. Okay, I guess that would make sense. So they did make a mistake. I promise you, I didn't make that slide. It's too good looking. Yes? Say that again? Nope, it doesn't affect anything else. All it affects is its S is now S1, and then it's full. So this is right. Copper. So what I'm saying, the word copper and the thing I'm explaining is true, but this slide is actually explaining it slightly different. It's saying a rule, but using the wrong example. So let's see what this slide says. Oh yeah, I almost forget. All right. This is because the 4s and 3d orbitals are very close in energy. These anomalies occur in the F block as well. And you won't ever get one of these. But just know it would rather rob one from the S that it's in and promote it to fill that F. You okay with that? Okay. You just take one number off of the S, so it's S1, and you add one more to the F. So it'd be 6S1 and then 4F14 instead of 4F13. Okay, I do have to explain this, even though the slides are a little bit weird. If you will look at right over here, so we're in the D's, right? 1, 2, 3, 4. So Boyd's right. That first slide, it was explaining this trend. Sorry, it was actually explaining this trend, but with this word, because there's actually 3 anomalies. So let me just make sure this would make sense. When we are 1, 2, 3, 4, when we're at chromium, if I were to draw the orbital diagram, it would have 1, 2, 3, 4, and it would have 2 in the S below it. You okay with that? It'd have the 2, and then 1, 2, 3, 4. It will do the same thing as we just said copper would. It takes 1 from here to half fill all 6 of these, because a half filled or fully filled is more stable than an empty shell. Okay, so the anomalies happen between here and here, between here and here, and it's just when they can complete something. All right, or from here to here, but I wouldn't really worry about the F's. They're never on test because you're never going to have to write. I can't remember YB, but nobelium. You're never going to have to do those. Yeah, uranium you have to do, but it's fine. It follows the conventional rules. Okay, are we sort of okay with those anomalies? You can read about them. It took about 6 minutes instead of 3. All right. we're not going to do this, but why do you think this is on this slide? It's the only math on the test. Chapter 6 test and 7 test are combined. Chapter 6 has this math question, which is worth a ton of points, but wasn't very hard, right? It has some electron configuration. It has some quantum number questions and some other stuff that when we review for it, I'll look more in detail. So that is finally the end of chapter 6. It's actually my favorite chapter of the year. And then chapter 7. Chapter 7, we're going to go way, 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 way faster than we did on chapter 6. Maybe like my YouTube video watching speed. What do you think, Reyes? That's bad? Okay. We won't then. All right. So this will kind of show you how far behind you are, but it's not that big a deal. Typically, we start chapter 7 a day or two before Thanksgiving, and you have to watch a series of videos. The first 2 of the 6 videos that I typically have you watch are the 2 I asked you to watch last time. Chapter 7 is a why chapter. Okay? When you're in normal chemistry, you have to tell me where the most reactive thing is, which is the bottom left and the top right. And that's all you have to do. In this class, you have to tell me where it is and why it's that way. Chapter 7 explains periodic trends. Almost every test question you can answer either with Zeff or electron repulsion. Those are almost always the answer. All right. Thank you, son. I almost called you son. Thank you, sir. That's funny. If you were really my kid, you would have complained about doing it the whole time. All right. I mean, I love them, of course. But they were way funner, the 2 older ones, before they turned something that ended with teen. All right. You can read about the periodic table. I'm done, so you just chill. There's some chairs there. You can sit in the back. You can just party and look good. All right. Okay. Elements in the same group generally have similar chemical properties. Properties are not identical, however. All right. Dmitri Mendeleev and Lothar Meyer independently came up on the same conclusion about how elements should be grouped. It was pretty cool. They did it years and years and years ago, and it still matches all the complicated stuff still to this day. Pretty awesome. That's what we talked about yesterday, right? Just for a second. All right. Mendeleev, for instance, predicted the discovery of germanium, which he called ecosilicon, as an element with an atomic weight between that of zinc and arsenic, but with chemical properties similar to those of silicon. So what that slide is saying is quite a few of these things didn't exist. Well, they existed. They hadn't been discovered yet when they made the periodic table. But the way they made it, they left holes. And those holes have been filled. And nothing that was newly discovered has ever displaced something that they had already organized. It's incredible. What's that?
In an afternoon.
Yes, in an afternoon.
Still works to this day.
Yeah. Well, that's a good poem. He said that it still works today even when new elements come into play. I'm going to get that tattooed on me. Okay, here we go. No, I won't. I'm scared of needles. All right, the periodic trends. In this chapter, we will rationalize the observed trends in sizes of atoms and ions, ionization energy, electron affinity, which really is more importantly electronegativity. Okay? So we're going to learn the trend and we're going to learn why. And it's not really that bad. So the very first and really most important part to learn at the start is what we call Zeff. Zeff is the effective nuclear charge. If you read this and watched the video, you should have a super good idea of what Zeff is. All right? In a many electron atom, electrons are both attracted to the nucleus and repelled by other electrons. So that's every single atom out there except for hydrogen. Hydrogen is the only one that does not have electron-electron repulsion. The nuclear charge that an electron experiences depends on those two factors. Now, nuclear charge, when you hear nuclear, you think of bombs, but we're just talking about the nucleus. The nuclear charge is this thing written here in my beautiful handwriting. It's the attractive force between the nucleus and the outermost electrons. And really it's for every electron, but we just talk about the outermost ones. Are we okay with that so far? It's a really important concept to get. So if we have an atom, we're basically saying how hard is the nucleus pulling on the electrons. That's what effective nuclear charge is. Okay? That pull depends on the balance of two factors. How many protons are in the middle, because that's the pluses. All right? And then how many electrons there are that are repelling the other electrons. All right. Permission to move on. Nope, you can sit over there. Enjoy. All right, I still see a lot of pencils. The electrons. Now, there's some complicated stuff coming up. Well, not nearly complicated as what we just did, so I guess it won't be that bad. But ultimately, everyone that's done this video so far got the answer right. Because ultimately, it wasn't very hard, right, Benson? You're like, all that crap, and it's just that number. Yeah, it is just that number, but we're going to spend a little bit of time to find that number. So here we go. So, the effective nuclear charge, which is Zeff, and there's a reason why it's called Zeff, and by the way, it's not Zeff, it's Z-effective. Z is the thing for protons. It's the nucleus, okay? So when we say Zeff, we're talking about this attraction from the nucleus. All right, the effective nuclear charge Zeff is found in this way. Zeff is equal to Z minus S, where Z is the atomic number. And that's easy to find. That's the smaller one in the box, right? Minus S, which is the screening constant, usually close to the number of inner electrons. And we say usually because sometimes it isn't, but in this class it always is. That isn't always, if you're okay with that. All right? So, Zeff, you have Z minus S. Z is the number of protons, which are positive. S is the number of core electrons, all right, which are your negatives. The core electrons are easy to find if you understand chemistry. The number of core electrons is equal to the atomic number of the previous noble gas. You remember when we've been doing the condensed, we put a noble gas? We put that in there because we were saying, hey, those are all full. They're not involved. All right? So, for instance, it looks like I chose sodium here. Sodium is element number 11. That's where this number came from. And then I go left on the periodic table, and there is nothing left, so I have to go to the way far right and the one above it, correct? So neon is the previous noble gas, and what's its atomic number? 10. So sodium's effective nuclear charge is 11 minus 10, which is 1. That's not too bad, right? All right. That's also the number of valence electrons. Or Zeff is also equal to just the family number. Yeah, and we will define it as the outermost 100% of the time in this class. All right. So there was another practice one right here. Chlorine was element number 17. The previous noble gas to chlorine is neon, correct? So you have 17 minus 10. So the effective nuclear charge on on chlorine is 7. Now, this charge of 1 or 7, it's not really a unit, but just know that this is way bigger than that. It's 7 times effective nuclear charge units. It relates to electronegativity, but not the same unit. What's that? Oh, absolutely. Yeah, good. If you've had science and you know what electronegativity is, they are definitely together. They're not the same, but they're chilling together. A high Zeff is a high electronegativity. A low Zeff is a low electronegativity. Electronegativity, and we'll learn about it. We're going a little out of order, but it's fine. Electronegativity is the ability of an atom to attract an electron to itself in a chemical bond. Okay? So one that is pulling 7 times harder on its outer electron than that one, it's going to get it. And look, we know Na and Cl actually bond to each other, don't they? And that's because when chlorine gets close enough to a sodium, sodium's holding on with one rubber band, essentially. And then chlorine comes by, and it's going to attach 7 rubber bands to that one. Who's going to win that force contest? Chlorine. Chlorine's going to take that electron because it has a higher effective nuclear charge or a larger electronegativity. Sodium's going to lose, and that's fine because we've been saying metals are what this whole year? They're losers. Now you know why they lose. It's because their effective nuclear charge is much smaller than a non-metal's effective nuclear charge. Okay? Now, will you do one for me? What is Zeff for phosphorus? That's an S. I don't know that I got any better. All right. So what's the Zeff? 5. It's 15 minus 10, which is 5. Or, if you know that phosphorus lives in the 5th family, you know that it's 5. Now, look at the periodic table for a minute. What's the Zeff of N? 5. What's AS? 5. What's SB? 5. So we don't care how low we go or high we go on the periodic table. This trend only cares left to right. Okay? For right now. What's that? Well, we don't. To do D's and F's, it's fine, but then we don't do them, first of all, because they don't really have family numbers. And they don't really, we have them, but you just do the same thing. Find how far they are away from the left, subtract, find their number, subtract that from their original previous noble gas, and it works. But we're not ever going to do D's and F's on this. You don't have to. Okay, are we all right with this so far? Finding Zeff? All right. Go ahead. AS, it's in family 5. I know. Because. And I know you're like, that's just bull crap. So what is 33 minus 18? 15. How many elements are in the D block? 10. So we just take that additional 10 and subtract. And then in the F's we do the 14. But like it gets confusing, so we just memorize equals the family number. All right, we okay with this? I know, whatever. Okay, so now we have something that we need to know. We need to know what Zeff is, and it's an attractive force, and we need to know the trend for Zeff as well. As we go towards the right, Zeff increases. I'm going to draw a lot of periodic tables and a lot of arrows over the next 2 or 3 days. If I draw one, you should write it. And then you should be able to explain why I just drew that arrow that way. So, Zeff increases as we move from left to right. And that is because, I got my wireless keyboard for this very moment. Because you guys complain that my handwriting sucks. What's that? Because my typing sucks? All right. Yeah, I thought it did work. Here we go. Oh, baby. Oh. Here we go. We'll go right there. That's a good question. They don't have 0 Zeffs. Yeah, but they're fine. The question is whether they have 8 or 0, because you go to the previous noble gas. And the question is, if it's 8 or 0, I don't care, because it's fine either way. Does that make sense? All right. So, why does Zeff increase as we move? It's because we add protons, but the core electrons stay the same.
Wow.
Boom! Eat it. There's your answer on the test. That's the why. And the why is very important. You're going to have to explain all these. They're going to be worth 5 points for each question. Telling me the trend is 2, telling me why the trend is 3. So you with me? Zeff increases as we go from left to right because we add protons to but the core stays the same. No, well, I'm not like scientifically adding protons, but I'm just, look at the screen over here for a second. I'm just saying that sodium has 11 protons, right? How many does magnesium have? 12. How many does aluminum have? 13. But every time in math, I'm still just subtracting 10, right? Because the core stays the same, but each additional atom I'm adding, there's another proton. We good? So there's more pluses, but the minuses don't offset it. And I didn't really talk much. It might be in the next couple of slides. All right? I wonder if you think this will work over right here. I'm going to guess no, but I mean, need sign. Oh. How about my no-look typing? It's taken me only 43 years to do that. I wasn't looking at the screen or the keyboard. It was like a piano player. Just how do you do that, Benson? You have to just memorize that fast? I swear there's like microchips in your fingers, and you just like program them, and you don't even think. Like the Bumblebee song. Have you played that? Yeah, that song is so fast, there's no way your brain is processing that. You're just barfing it out on your fingers. Yeah, that's incredible. My kid plays that. I'm like, dang, Gina. His name's Dallin, though. Whatever. Dang, Gina's an old show. Okay, let me talk about this, if it's not. Okay. We need to understand. And there's a whole section on the, well, it's a whole nice paragraph on S. what we have, just stick with me here, we have the protons or the nucleus, and we have electrons here that are chilling. And if those are the only two we have, they are simply pulled here and here, but each one of them sort of pushes the other one away at the same time. You okay with that? Like, they're fighting a little bit. Kind of, yeah, you can put it that way. Now, if there's only two, they're not really fighting that much. But they kind of are, and that's helium. You with me? But then we add another level, and now we have electrons here and electrons here. If we're talking about this, in this example, our S is equal to 2, right? It's these two. Are you okay with that? Okay. So what we're saying, S is called the screening or shielding constant. They're both the same thing. And what it's saying is that the inner core electrons, they push the outer electron away. Okay with that? This electron is attracted to this nucleus, but can't get as close as that one does because that negative pushes it away. You okay with that? So hold on. So the first atom I drew must be smaller than when I added that second one, right? Because these electrons repel. What S is saying is that core electrons shield the nucleus from the valence electrons. All right, go ahead. They still just repel. But they can go into different shapes of clouds or swap. So sort of both can happen. But generally they just repel and stay in their same shells. All right. So this is why we care about the core electrons. If the core electrons stay the same, the screening effect stays the same. But if we're adding more positives, we're getting more attractive force. Okay, here we go. What this has to do is with our next trend. Well, we better draw this too. All right. Zeff increases as we go up in a periodic table. And this one's way less important to know, but you should know that. So if it increases as we go right and up, what's our smallest atom? Helium is. Now fluorine's super small also, but it has so many more protons and electrons, it has to be bigger. But helium is actually smaller. Everyone will say that hydrogen is the lightest atom that exists, and that's true. But they rarely say hydrogen is the smallest atom that exists, because that's not true. All right? Now, there's 2 electrons, so it's an extremely close size, all right, for H and He. But Zeff increased over here. It increases over here. So these are your small atoms, and these are your big atoms. Are you okay with that? Zeff decrease as we go down. You have to know that also. In the first one. No. Well, sort of, but not really. Uh-oh. What? That's what I'm on right now, if I can find where the freaking delete button is. Shoot! That's what I was doing, but it wasn't registering. Now, the arrows are working. Okay, come on, backspace. Okay. That's what I was doing, but it wouldn't work. But the arrows would move. All right. So this is the Y for the up and down. Because as, oh my, geez Louise, what? What word am I on? As we move down, Oh, shiz. Whatever. I don't want that capital. Don't give me what in the world. That's not that bad. Because as we move down on the periodic table, we are adding principal energy levels, which is N. Remember that number? I'll come back there. Oh, that's just a disaster. Principal energy levels, N, or more shells equals larger atoms. Then, remember the very start? I said, hey, there's pretty much two answers to every question. Zeff or, remember the other one? No, so close though. There's more electron-electron repulsion. You can... Oh, that's just wrong because there's two of them in a row, right? Okay. Now, this is going to affect the size of atoms. You need to know the size of atom trends, which are similar to the trends for Zeff, because it's all about Zeff. Because if you have greater attraction from the nucleus to the outermost electron, then it will hold it closer. If you have less, then it holds it farther away. We define the size of an atom by the distance from the nucleus to the outermost electron. Please watch those two videos tonight and read. Yeah, if you have